All right. Welcome everyone to the first part in a two-part series on the unsteady panel method, which is basically a continuation of the steady panel method that we went over last module. So to start off, let me do a little review and compare the steady panel method to the unsteady one. In the unsteady panel method, we basically solve for the steady or terminal scenario, i.e. if you have a wing that's traveling at a certain free stream velocity, we don't capture the entire scenario starting from rest. We just look at the final sort of steady case of the entire phenomena. So when we do this, we really cannot model airfoil unsteadiness, such as the start of a motion, or even capturing unsteady maneuvers like pitching or surging, plunging, all that stuff. We also do not time step. We just look at the final case or the final time step, essentially. We do not time step or march in time. The second thing we have is that we solve this problem by meeting two boundary conditions, namely the no penetration boundary condition, as well as the kata condition, which says that the flow at the trailing edge has to leave the trailing edge smoothly. And finally, we only model the bound vortex sheet. So we don't model the wake that is shed from the wing. So there is really not much vortex interactions captured in the steady model or the steady in the steady problem. Now, in contrast, in the unsteady panel method, we do solve for the entire unsteady case. So we solve for the entire unsteady scenario. So if we want to, for example, capture the free stream velocity of a wing, then we solve the problem starting from rest up until the wing reaches the required velocity, and we march in time until we get to the steady case. So the steady panel method, we jump directly to the steady case. In the unsteady panel method, we march in time from t equals 0 until we finally reach the steady case. So using this model, we can actually can model arbitrary airfoil motion, which means that you can model a wing that's pitching or changing velocity in time. You can also model a wing that's, for example, deforming or changing its camber, or a wing that has a flap, maybe a trailing edge flap that you can sort of change its deflection in time. So you can model a lot of unsteady situations. And as we said before, it involves time stepping. Now, in this model, we actually satisfy three boundary conditions. And the first two boundary conditions are the same ones that we have satisfied from the steady panel method, which is the no penetration in the color condition. The final one is Kelvin's circulation theorem, which says that the circulation of a system is always conserved, i.e. the entire circulation, the time derivative of the circulation in the entire system, isolated system, is always 0. And finally, in contrast with the earlier method where we only model the bound vortex sheet, here we model both the bound vortex sheet and the shed wake. So the vorticity that's shed from the wing, which means that we have significant vortex interactions or interaction. So we basically have a sort of a coupling or a two-way street of interaction between the bound vortex sheet and the shed wake. So both affect each other, and the influence of one on the other will affect the evolution of the vorticity in the system through time. So this is a really important point to keep in mind. So to start off, a really important thing in this in the unsteady panel method is being able to easily transfer between frames of references, because we will, in contrast with the steady panel method, where we have only worked in the wing fixed frame, which is this one. We didn't need to change frames of reference. We just purely worked in the wing fixed frame. Here we are going to do things differently, where we will still use the wing fixed frame to, for example, calculate your influence coefficients and all that stuff. But we will need to do a significant amount of stuff in the inertial frame, like the propagation of vorticity and kinematics and all that. So we need to be able to switch between frames easily. And here I have a simple diagram, well, relatively simple, to try to explain how to transfer between the two frames of references. So the wing fixed frame is essentially a frame in which the axis, which is given here, is attached to the wing and moves with the wing. On the opposite hand, the inertial frame of reference is independent of the wing. So the wing, this axis can essentially see the wing moving, whereas this one, not really, because it's always moving with the wing. So here we have the wing fixed frame attached to the leading edge. So the origin of the wing fixed frame is at the leading edge, but you can put it at any other point on the wing. Essentially, the only difference is that if we have the wing fixed frame origin at the leading edge, then if we have a pitching wing situation, we would be pitching about the leading edge. In contrast with that, if you put the origin to, for example, the midchord, then that means that if you do any pitch maneuvers, those pitch maneuvers would be about the midchord. All right, having said that, we let's say we have some arbitrary point P, right, that is expressed in the in the wing fixed frame. And we want to determine this point in the inertial frame. So the transformation between the wing fixed frame and the inertial frame has two steps. The first step is, as you can see, this wing fixed frame is at an angle to the inertial frame. So it's rotated with respect to the inertial frame. So the first step to transforming this P position from the wing fixed frame to the inertial frame is to rotate the wing fixed frame with alpha, angle of attack, so that it can be represented in the inertial frame. And I'll go over the actual rotation in a little bit. So after we move and rotate this axis to the inertial frame, we get this vector. So we have this vector, and essentially the main vector we are interested in is the position of P relative to the origin of the inertial axis. So all you need to do to get that is simply add the vector you obtained when you rotated the wing fixed frame to the inertial axis angle, and then you add the position of the origin of the wing fixed frame with respect to the inertial axis. So let me try to sort of write this down to give you a sense, and so that things are not that abstract. Let me switch to, say, blue. So the first thing, as I said, is that we need to try to rotate the wing fixed frame to the inertial frame. So the rotation is basically, the amount of rotation is basically the value of the angle of attack of the wing. So the rotation matrix from wing to the inertial frame is simply equal to cosine alpha sine alpha minus sine alpha and cosine alpha. And if you've taken flight dynamics or a dynamics course, you're probably aware or have seen these rotation matrices before. I'm not going to spend too much time on them, just so that, just for the sake of time. But if you have any questions, just please let me know and we can discuss this. All right, so how do you go from the wing fixed frame to the inertial frame? First step is, again, rotate the coordinates of P in the wing fixed frame by the angle of attack alpha. So let's assume that P has the coordinates small x, lowercase x, lowercase z. You multiply this by the rotation matrix to get the rotation. And as we said before, after you rotate the vector P from the wing fixed frame to the inertial frame, you have to add the offset between the origin of the inertial fixed frame and the origin of the wing fixed frame. So we're going to add this right here, XO and ZO, both uppercase, which represent essentially this vector. And that's it. This is your coordinates of P in the inertial frame. All right. So we're not only interested in positions, but we're also interested in velocities. So we need to take the derivative, or we need to sort of have a representation of the time derivative of the position P in the inertial frame. Now, again, if you take the derivative of this expression here, well, it's sort of a product rule, because the rotation matrix R contains alpha, and alpha is a function of time, and X and Z are basically the positions in the wing fixed frame, which is always fixed to the wing. So the only time you'll have an X dot or Z dot is if your camber is changing with time. So if you have a camber like this, and this is small x, and then small z, If this camber is a function of time, then you have an x dot and z dot. But if not, if you have a non-changing camber, or you have no flaps that deflect, then you have no time derivative in the x, in the small x and small z coordinates. However, I mean, you can always have time derivative in x naught and z naught given the velocity of the wing, because as the wing moves up and down, this vector, which is the offset between the leading edge in this case and the inertial frame, that changes in time. So let's sort of, let's take the derivative of that, right? So the derivative is, so this is a simple product rule, right? So x dot, z dot, right here, plus now we take the derivative of the rotation matrix, I times the vector xz plus x dot and z dot, big X and big Z, which essentially represent the velocities of the wing in the x direction and the z direction. All right. So moving on. Now, as we have said, this here represents basically camber change. If your camber changes in time, so the wing airfoil changes in time, or if you have a flap at the end of the wing, right, that sort of changes in time. This here is related to pitching. So if you have an alpha dot term, if you're pitching, then this term is non-zero. So this is 0 if alpha dot is equal to 0. And since we attached our wing fixed frame to the leading edge, any pitching would happen on the leading edge. However, if you want to pitch about some other point, all you have to do is, in your formulation, move the origin of the wing fixed frame to that point. And then finally, this represents the wing velocity. All right, great. So now you can take this formulation and turn it into a function, right? You can create a function. So a function that would take a function that would spit out x and z in the inertial frame and their time derivatives in the inertial frame, right? And then WTI, or so I'm saying wing to inertial, WTI, but this function will take small x, small z, their time derivative, your origin position, so x naught and z naught, so the origin of the wing fixed frame to the inertial frame, the relative position between both, as well as their time derivatives, or essentially the velocity of the wing. So, and not to forget alpha and alpha dot if you have pitching. So all we did here is we have taken this formulation and we have formulated it into a MATLAB function. All right, so now that we have looked at how to transform a vector P from the wing fixed frame to the inertial frame, let's try to do the opposite. So the opposite is actually pretty simple. To start off, I'm going to give you the rotation matrix that takes you from the inertial to the wing fixed frame. And this is simply cosine alpha minus sine alpha over sine alpha cosine alpha. All right, so essentially, again, we are going to do the reverse process. So we're going to have this big x, z, right, vector. So first thing, remember again, we've rotated and then we've added this vector to get from the wing fixed frame to the inertial frame. So now we're going to take this vector, subtract this, subtract the position of the wing fixed frame origin, or the leading edge here, from the origin of the inertial frame, which is done here. And then we are going to rotate this axis now, or this vector, we're going to rotate it like in the opposite direction by the same amount alpha. So, and that's done by this sort of rotation matrix. So we're going to multiply this vector by r from inertial to wing. And this will give you basically x and z in the wing fixed frame. All right, just sort of expanding this expression gives you this right here. All right, where x and z are functions of time, x naught, z naught is also a function of time, and the matrix, the rotation matrix, is a function of time if we have a pitching maneuver. So yeah, let's try to get the time derivative of this expression. X dot and z dot is equal to, again, this is a product rule, so r of I to w of x dot and z dot plus r dot of I and w, and I'm just taking the derivative of the expression above, w of x naught, z dot naught, minus r dot from inertial to wing of x naught and z naught. You would have these components if you have pitching, i.e. if alpha dot is not equal to 0. And as you can see, if you don't have any pitching, then we only have these two components right here. But if we have no camber change, then x dot and z dot should be equal to 0, because the camber is not changing in the frame of reference of the wing or the wing fixed frame. Well, if the camber is not changing, then if we have then the wing is rigid, meaning that any velocity that's traveled by the wing will be the same velocity of each point on the wing, x and z. And thus, these two would subtract out, which would give you x dot and z dot equal to 0. So, as I said before, this sort of expression here gives you the position or the time change of position of any position along the camber or along the wing. And if the wing is rigid, it's not changing its shape, then these go to 0, because these are in the wing fixed frame. So this is an important point that I want to make sure that I convey, is for a All right, I'm just gonna write it down here. For a rigid wing, i.e. a wing that does not deform, the camber line doesn't change, you have no trailing edge flaps, X and Z are equal to constants. So X and Z, or any position on the wing with respect to the wing frame, this is always the same. However, but X and Z are not constant, because the wing itself is moving relative to the inertial frame. All right, so again, the same thing we did. You can create a function for that one. So say function takes spits out small x, small z, x dot, z dot, and this would be equal to ITW, or inertial 2 wing, of x and z, which are any position in the inertial frame or any position along the wing, its time derivative, and then x0, z0, x naught dot, z naught dot, which is the velocity information of the wing itself, and alpha dot. All right, so I don't think you were gonna use this function much, but it's good to keep it in your head, or good to know. And finally, we create a third function that transforms the unit vector from wing fixed frame to the inertial frame. So for instance, in the steady panel method, we derived the tangential unit vector along the surface of the wing, as well as the normal unit vector along the surface of the wing. So here, this is simply a function that rotates your these unit vectors from the wing fixed frame to the inertial frame. So yeah, you take the rotation matrix from wing to inertial, and then you simply multiply it by the said vector. So this is a 2 times 1 vector containing the tangential and normal unit vector in the wing fixed frame and inertial frame. So I'm just gonna write this down here. The function of, or the function of this function is to rotate the n and t hat to inertial frame. Great. So we went over this. Now we can actually start talking about the algorithm. So first things first, I'm going to write this in black, but I'm gonna suggest a method with which to sort of work or save the data and work with it. Suggested way to save data. And this is the way I do it, but you're welcome to do it in any other way, any way you see fit. So I save the data in structures. So each entity in the code has a structure. So the bound vortices, they have a structure, the collocation points, the corner points. So here I have VB, which is the bound vortex sheet structure. VS is the shed vortices structure. The COL is the collocation point structure. and COR is the corner point structure. So these structures contain the position information as well as the vortex strength information, if applicable. The positions in these structures for the vortex sheet is in the inertial frame for the shed vortices, and inertial frame for the collocation points, and wing fixed frame for the corner points, because just so that you have the contour of the camber you're using in the wing fixed frame. And using this method to sort of save the data makes it easier to track time history. So you can basically save the vortex sheet information, the shed vortices information, and all that for each time step. So you can save the information regarding the evolution of the aerodynamic system you're working with. And I'm gonna give you an example on how to save one of the structures. So let's say we are working with the bound vortex sheet structure, VB. So let's look at the X position in the vortex sheet. So VB of I, this index here, indicates the ith time snapshot, right? And then J is the jth, the position, the X position of jth vortex. And then you can also save, you can do the same for the Y position of that vortex, and also the vortex strength of this vortex. So all these expressions here are related to the same vortex. All right, so this is the X position, Y position, and vortex strength of the jth vortex in the ith snapshot of time. Now we're gonna start looking at the skeleton of our code. So one thing is I want to say is that it is useful to break down the code we're working with to several functions or scripts called within a main script. So instead of having a long main script that contains everything, you can break down each step of the algorithm into its own function or its own script, and call these scripts and functions in a main script, and that will make it easier to debug the code and work with the code and make alterations or modifications to your codes. So I mean, in this code we want to define the angle of attack alpha, the free stream, possibly rho or density, the chord length, n, which is the number of corner points, dt, and it max. So I'm going to give you definitions of these. This is the number of iterations. So if this value is, say, 100, that means that you are going to march 100 time steps forward. And dt is the length of the time step we use. N is number of corner points. And this one is the chord length in meters. And then these ones, rho, U infinity, and alpha should be self-explanatory. Great. So let's start moving into the actual code or script. So we start off with a for loop. And this for loop marches us in time. So we're gonna march in time. We're gonna run a number of loops that is equal to the maximum number of iterations we are working with. And then for a specific loop, the time step we're on is basically just the specific number in the loop that we're in. So the number of iteration we're in multiplied by dt. And to explain that, basically, if you are, let's say you're running 100 loops, and you are currently on the 10th loop. On the 10th loop, t will equal to the number 10 because you are on the 10th loop multiplied by dt, or the length of one time step. Great. So moving on, the first function or first step is the geometry function, which, if you recall, in the steady panel method, we used we had to come up, given a specific wing, we had to come up with the corner points, then the coordinates of the bound vortices and collocation points, as well as the normal and tangential unit vectors. So we're going to do all that here. I'm going to go back to blue. So this function is used to find corner points, assign collocation points and bound vortices, and you also find the normal and tangential unit vectors in the wing frame. And it's basically the same thing we used to find these things in the steady method. So same as steady method. But may need to store time history. Of these points. So as we said, as we said before, this is an unsteady model or unsteady algorithm, and thus it would be important for us to save the time history or evolution information of our system, so we can look at the time rates of change of things and look at how the shed vorticity evolves in time, and look at the vortex formation and all these things. So it's important to have a system with which we can save the time information. And we are going to save so we're going to save to corner points, structure, bound vortex, structure, and collocation point structure. All right, so the second step is defining the kinematics of the wing. So in here we define wing kinematics. Sorry, I forgot to put an M there. Define wing kinematics, such as position, velocity, and angle of attack and pitch rate. Right, and as we remember, angle of attack is really also it's the angle of attack of the wing, but also in our formulation, it's the angle between the wing, fixed frame, and inertial frame. All right, so, I mean, just to put it symbolically, you're trying to find XO, define ZO, which is the vertical position, alpha, and then their time derivatives, all in the, as you can see, in the inertial frame. So you basically, even though you found your corner points in your wing fixed frame, because it's easier to actually define your camber line in the wing fixed frame, we define the kinematics of the wing itself in the inertial frame. So to give an example on what these kinematics might look like, let's say you have a wing that's impulsively started from rest, which means that it means that you have a wing which at t equal to 0 is at rest, but at any time beyond t equal to 0, it's at a constant velocity. So the velocity of this wing looks something like that, where this is v and this is time. So for any time before 0, it's at rest, but then as soon as you pass t equals 0, you hit a free stream velocity. So it looks like that. So this is your wing. It's at a certain alpha angle of attack, and it's traveling at a constant velocity u infinity. In this case, x naught, since this is traveling at a constant velocity, x naught is minus u infinity t, because if this is your inertial axis, let's say we are defining our inertial axis here, which is something you can perfectly do. You don't have to have your inertial axis offset from your leading edge. You can have it right on the leading edge. So if this is your axis and your free stream velocity is u infinity to the left, that means that your velocity vector is negative because it's going opposite to the x-axis, and your position is your velocity multiplied by time. So x naught is equal to minus u infinity t. We also know that alpha is equal to some constant. It could be 5 degrees, 10 degrees, whatever you want. And then, sorry about that. And then x naught dot, which is essentially your velocity in the x direction, is simply just a negative of the free stream. And then z naught is equal to z dot naught equal to alpha dot, which is equal to 0. Now z naught is equal to 0 because, as you can see, the origin so the leading edge is on the origin of the inertial frame. So it's at y, sorry, not y, I'll fix that. So the origin itself is the leading edge is on the z-axis. So the leading edge is right on the origin. So z naught is equal to 0. There is no vertical velocity. The wing is not going up or down. So z naught dot is equal to 0. And if you're not pitching, then alpha dot also goes to 0. So this is an example of what your kinematics might look like. If you're pitching, if you have an acceleration, a linear acceleration profile or something like that, you can change the kinematics prescribed accordingly. And now the third step is transform coordinates. So in this step, you transform all coordinates and vectors, meaning all coordinates, velocity vectors, and unit vectors from wing fixed frame to inertial frame. And then after doing so, you can save this information to the collocation structure and the vortex sheet structure. So save the inertial positions to your structures. All right, so the fourth step is the shedding process, or placing the, so as we march in time, every new time step, we shed a vortex from the trailing edge. So in this step, we will place the vortex in the flow field, the newly shed vortex in the flow field, but with an unknown vortex strength. And in the solution of the sort of the linear systems of equations, like the one we had in the steady state scenario, we will solve for the vortex sheet strength as well as for the strength of the newly shed vortex. So here we're just simply placing the new vortex. This function defines the position of a newly shed vortex, but with an unknown strength. And again, this strength will be determined when we solve the linear system of equations. So the question is where to place vortex. So we want to place the newly shed vortex in some position in the vicinity of the trailing edge that's basically not too close to the trailing edge, not too far from the trailing edge. So one way to do it is we can position or place that newly shed vortex along the trailing edge path 0.3 times the distance traveled by trailing edge between t and t plus delta t. So an example on this, say we have a wing that's in this position at t and moves to this position at t plus delta t. Now the trailing edge has moved this much, moved by a distance of the free stream times delta t, or that's in the case of a constant free stream, but in a sense it has moved some distance, and depending on what you're solving for, depending on the problem you're solving, you know how much the trailing edge has traveled, and you know the path along which the trailing edge has traveled. So you basically place the vortex along the trailing edge path in 1/3 or 0. Well, this is not exactly what this is, but let's say we place it 0.3 times the distance traveled by the trailing edge and along the trailing edge path. So, for example, this is the path that the trailing edge has traveled between t and t plus delta t. This is how much the trailing edge has traveled, the free stream times delta t. So we place the the trailing edge newly shed vortex along the path at a distance of 0.3 multiplied by the distance traveled in that time step. So I hope this sort of makes things a little bit clearer. So we have determined the x and y position of this vortex, but not the vortex sheet, not the vortex strength of the newly shed vortex yet. Great. So in this step, we save the vortex position to the VS structure. Of course, we found this position in the inertial frame, so let me put that down. It's the inertial position of that vortex. Great. So, as we know, in every time step, a new vortex is shed, or a new vortex element is shed. That means that the VS structure or let me reword that. That means that the vector within VS structure increases by one element every time step, because we are storing all these shed vortices in a vector within that structure. So the vector at time step t will be one element less in length than the vector containing the shed vortices at t plus delta t. So let me give a concrete example just to illustrate this point. Let's give an example where you're accessing the structure of the shed vortices at the third time snapshot, and we're looking at the vector, we're looking at the x position vector of the vortices. Let's say this is equal to x1, x2, x3, meaning that we have three vortices that have been shed in the flow, and these positions are at time step equal to n. That means that at the following time step, let's say time snapshot 4 or I equal to 4 of the x positions, the vector will include all the prior sort of vortices that were in the previous time step, but at their new locations at time step n plus 1, plus another one, or in addition to another vortex here, which corresponds to the position of the newly shed vortex. So in that sense, as we march in time from one time snapshot to another time snapshot, our vectors of our x, y, and vortex strength vectors will increase by one element at every time snapshot, because you are shedding one new vortex at every time step. So with that said, that brings us to the end of part 1 of the lecture And in the second part, we will go over how to construct the coefficient matrix, matrix A, and the right-hand side vector, as well as solving for the lift, solving the systems of equation, and also finding the and also convecting the wake. Thank you.